to do that. So okay, so there's our answer right there, isn't it? Everybody agree? S of n. Now where did we get that from? Well, look at R of n up here. R of n, that's just where we started right there. You see that? It's just before we use those fancy summation formulas. Remember where I said you can just use technology to add something up? Right, there it is. There's R of n right there, depending on the value of n we pick. But I would have to use technology there because that means nothing to any of us at this point. If I just look at this, that expression, you know, we don't know. If I plug in a certain value of n, who knows what that is? I still have i's in my answer, right? But we did the math, and we found out that if we use the summation formulas and we get rid of the i's, we actually add up those sums. We get this result. Okay. Well, I want to show you a couple things here. First of all, if we just add up R of n, look what we're getting over here in our graph. Okay, that's the, if n is equal to 1, that's the area we get. If n equals 2, that's the area we get. If we choose n equals 3, that's the area we get. Actually, I think maybe n equals 1 is clear up there, right? Okay, now watch what happens if I let the number n increase. Okay, let me go up here and I guess I gotta do this. N equals 4. Oh, I can't do that, huh? Oh, I don't have to. Never mind. All I gotta do is add more rows to the chart. Okay. What's it doing? It's approaching the limit, isn't it? Look, each time I add another rectangle, I'm getting incrementally closer to my answer. Well, what do you think my answer is going to be? Well, I got it down to 21.57. And if I were to keep going for a long time, I could maybe get it a lot closer. Okay. Well, one thing I want you to notice is, first of all, let's just check and make sure that our fancy summation formula works. Right? There's our summation formula. If I turn that one on, oh, what do you know? It overlaps perfectly. So it did work. Okay? That's a lot easier than that, though, isn't it? This requires huge technology. This one doesn't so much, right? That one's pretty easy. Okay? In fact, what do you think's going to happen with that one? Look at the form of our answer, and you tell me what's going to happen if I take a limit here as n goes to infinity. It's going to go to 21, right? If I take a limit as n goes to infinity, look what happens, right? I'm going to end up getting 45 over 2n is going to go to 0. 9 over 2n squared is going to go to 0. I get the exact answer, 21. About that. That's pretty cool, right? Now, we couldn't do that. I just want you to appreciate how important it was that we actually went the extra mile and used those summation formulas, right? I couldn't have done that there. If I take the limit here as n goes to infinity, who knows what happens, right? Everything blows up. So I've got n's inside of my sigmas, and it's crazy, right? So it doesn't really work. Okay? But if once I utilize those summation formulas and I write this as a function of n only, so there's no other i's in there contaminating, then I can take that limit pretty easily, right? Okay, if I were to plug in, I just happen to have done the left limit also. Okay, so if we add another column here, what do you notice? If we use the left limit and the right limit, the left limit starts off undershooting massively, the right limit starts off overshooting massively, but as the number of rectangles increases, they both converge on the same answer, don't they? Okay, that's really significant. That tells us then that we don't really have to be picky. If we're going to or we don't have to be, well, we can be picky, I should say. we can pick and choose whichever one is the most convenient one. If we're going to let the number of rectangles go to infinity anyway, let's just use the most convenient way to sum up the rectangles, right? Because they're going to give us an exact answer anyway, right? So there's a specific name for this concept. A Riemann sum is just what you get when you sum up an infinite number of rectangles over some interval to calculate an area, right? Now, technically speaking, if you want to use the most general and technical form of a Riemann sum, well, instead of x sub I, we just use c sub I. And c sub I it could be any point in the ith subinterval. And of course it doesn't matter, because as the length of the rectangles go to 0, any point in the ith subinterval is the exact point that's going to correspond to the height of the function, right? So it doesn't matter. I always tell my students to think about c as c sub I equals convenient, which means x sub I. It's the most convenient one, the right edge. It's the easiest one to sum. And delta x sub I is the length of the ith subinterval. So it accounts for the possibility that the subintervals are not uniform lengths. But once again, it doesn't make any difference, so let's take the convenient approach and let them all be the same width, right? Why not? We're going to get the right answer either way, okay? Okay, so next step then is, and this is just the coolest thing ever. So now we want to be completely general. We said from 1 to 4 last time, right? Let's not. Let's take the specific function x squared. That's as specific as we're going to get, but we're going to let the left endpoint be a and the right endpoint be b, and we're going to come up with a completely general answer for the area under the curve, right? And once again, I'm not going to burden you with all the algebra. I did that. But it looks very much the same, right? Only difference is we can't plug in 3 for b minus a, but everything else should look pretty similar, right? Okay, we expand it all out. If I take, f of tan is just tan squared. Well, if I square out that whole big ugly expression, I promise you, that's what you get right there, okay? So we can break that up. We can break that up into separate sums, and I can take everything that doesn't have an I in it out in front of the sigma, and then I get my same summation formulas that I had before, right? And if I do all the same stuff, essentially, I'm just going to still cancel the 2's. I'm going to cancel the n's there. I'm going to reduce the, okay, I guess I can't reduce that one, can I? I can't really cancel any numbers there, but I can cancel an n, I can cancel an n. And as the dust starts to settle here, what happens? Well, okay, this reduces to an n plus 1 over n. This reduces to an n plus 1 times 2n plus 1 over 6n squared, if I pull the n squared in there. And if I do a little math with this, if I expand all this out and break it into separate terms, it looks like this: 1/3 plus 1 over 2n plus 1 over 6n squared. If I multiply out the top and split the fractions. Okay, I can do some stuff with this. I can go ahead and, at this point, I could go ahead and take my limit, right? The i's are all gone. I can take my limit as n goes to infinity. Every term with an n on the bottom is going to go to 0, right? And I get that. Well, that's looking a lot better. Looking a lot better. Okay, so what can I do here? Well, let's get a common denominator. Let's multiply each of these by 3 over 3. Well, I guess I can cancel. If I distribute the a, I can cancel the a squareds. That's good. And if I multiply this by 3 over 3, I just get 3 times ab plus all this stuff over the common denominator 3. Okay, let's add up like terms. What do we end up with? If I add up like terms, I've got 3ab minus 2ab is just ab. I've got a b squared, I've got an a squared, and at this point, let's just pull that 3 out front as a 1/3. Okay, does that look familiar to you?
It's if you took it off the square.
No. That's the factored form of what? Going back to probably algebra 2 is where we would have done a lot of this.
Cube minus that constant.
It's gonna be, that's the factored form of b cubed minus a cubed, right? It's a difference of cubes. Does that ring a bell? okay? So, that's pretty amazing. Now this is starting to get, now look where we started. Already, you know, assuming we did everything right, and it worked, so it is right. Look where we started with this. Okay? Ugly, but it's starting to look good, right? Which is, just trust me, in math and in physics, when things start to look good like that, that's when you know that those 20 pages of algebra you did, okay, something's working. If it's that simple, I must have been doing things right. I'm not kidding. That's the way sometimes you look at it. If things start to work out, then okay, I'm probably doing something right here. Well, let's review something. So we're looking for the area under f of x equals x squared, right, on a to b. Okay, so going back to our definition of an antiderivative or an integral. Well, we said that the antiderivative of f of x dx is equal to something that we're going to call an antiderivative plus some constant of integration, right? Okay, well, what's the antiderivative of x squared?
X cubed over 3.
Aha, x cubed over 3, right? If we ignore the constant and we look at just the antiderivative part, the antiderivative of x squared is x cubed over 3. Do you see something there?
X is the fourth over 12.
Well, but look what we got. We got b cubed minus a cubed over 3, which is the same thing as b cubed over 3 minus a cubed over 3.
So b squared minus a squared.
Well, no, but what are we trying to do? We're trying to add up the area under x squared from x equals a to x equals b. Doesn't, look at that. That's in the form of the antiderivative, isn't it? Okay, here's a way we can say this in calculus. It's just equal to x cubed over 3 evaluated from a to b. When you see that notation in calculus, what it means is this expression, it's going to be the difference of this expression evaluated at b minus this expression evaluated at a. There's literally a notation for that because we do it so often in calculus. That's huge, right? What a great trick. All we would have had to have done here then, if we wanted to answer this based on the work we just did, and this is not an isolated example, it would have worked for any function we picked. I mean, this isn't a rigorous proof because I'm just demonstrating that it works for a certain function, right? We didn't leave the function completely general that we picked. We picked x squared. But look what that's telling us. This is the fundamental theorem of calculus. We got there. Okay, if I want to add up the area, if I want to add up the area under a function from x equals a to x equals b, it literally is the result of taking an antiderivative. Now this is a different kind of antiderivative. Instead of the kind that we had clear back like 20-some pages ago, right there, this is what we call an indefinite integral because I've got a plus c at the end of it, right? Or an antiderivative. If I take the antiderivative of f of x by doing the indefinite integral of f of x dx, I just get f of x, which is the antiderivative, plus c, the constant of integration, right? Well, in this context, it does something a little bit different. It does something a little bit different because this time we're not wanting to get back the antiderivative function. We specifically want a number. We want the area under the curve, right? And so we write our integral a little bit differently. This is what we'd call a definite integral. Okay, so here's the function under which we're adding up area. The limits of integration, the lower limit goes on the bottom of the integral sign, the upper limit goes on the top of the integral sign. But the answer is just the antiderivative of f of x evaluated at b minus the antiderivative of f of x evaluated at a, okay? Which we can, there's kind of a shorthand notation for that. But a lot of books won't even say that. A lot of books will just leave it at this, okay? That's huge. We can do a problem, like here's a new problem that would have taken us forever. Would have taken us 2 periods to do starting yesterday, but you can do it right now. I want the area under, let's do the area under x cubed from -1 to 6. We can do it in about 5 seconds. Maybe it's more than 5 seconds, but not much. How do I set that up?
Take the integral that's cubed.
So I'm going to do the integral of x cubed dx from,
-1 to 6.
right? And so that's equal to, well, what is the antiderivative of x cubed?
X equals 4.
Evaluated from -1 to 6. So it's literally, this is the answer. It is 6 to the 4th over 4 minus -1 to the 4th over 4. That's it. That's the area under the curve. Exact area. It's not an approximate area, because we got there by letting the number of rectangles go to infinity, right, taking that limit. Okay? So you can kind of, maybe you can see what I talked to you yesterday about. You know, we're getting to some place where things get a lot easier, right? We can use this trick now to add up areas under curves. And so now we can spend the rest of the year kind of focusing on, okay, how do we apply the fundamental theorem of calculus and doing some problems that help to get better at using that? Because in reality, as an engineer or, you know, as a physicist, or when you start actually applying this, you will never write it out this way. You'll never do it once, because it's, why would you, right? It evolves to a much simpler, you know, a much simpler form, the fundamental theorem of calculus. Okay? Just try one of these on your own here. Try, see if you can do this one. How about, let's do, let me help you come up with, see a pattern. So how about this one? What if we do, okay, let's do the integral of x squared. We're going to add up the area under x squared from -3 to 3. Okay, so how am I going to, so what's the form of my answer here?
3 cubed of 2 minus -3 cubed of 3.
Well, let's do the whole thing. So by a show of hands here. So what's going to be the form of my answer? What's the fundamental theorem of calculus telling me here, Ryan? What's that equal to? Don't try to give me a full answer, but what's the antiderivative of x squared?
X cubed of
Okay. X cubed over 3, evaluated from -3 to 3. Okay. All right. Sparhide, what's the?
3 cubed over 3.
Okay, so we're going to get, that's going to give us 3 cubed over 3 minus -3 cubed. Okay, right? And so that's going to give us, if we do the math, what's 3 cubed over 3? 9. Same thing as 3 squared, right? So we're going to get 9 minus, what's -3 cubed over 3?
-9.
18. Okay. Is it an accident that I got the same number here as I got here when I subtracted the negative? It's not. It's not. If I have symmetric limits, let's look at why that might be. Here's a little trick you can do. If we take a function like x squared, now what's significant about x squared? Why did I pick x squared?
It's symmetrical.
Okay, what kind of symmetry?
X.
No, what do we call that? But what's the name of that?
Around the y-axis.
Okay, but we have a simpler name for that, right? Even symmetry. Right? It's even symmetry, so it's symmetry about the line symmetry about the y-axis, right? So if I look at the area under the curve, now this is obviously not to scale, but if it's an even function and it's got symmetry about the y-axis, then, and I have symmetric limits of integration, then can't you guarantee that both of those areas are going to be the same, right? And so really what I could do is I could say, well, okay, instead of doing that problem, I could do this problem. This is a better problem. Why is that such a better problem?
It's half the work.
Okay, but I still have an upper limit and a lower limit.
First one just goes to 0.
Yeah, right, it's easy to evaluate stuff at 0, right? So that's gonna give us 3 cubed over 3 minus 0 cubed over 3, which is, see what I'm saying? I've just got 2 times that, right? So we could generalize that and we could say if f of x is even, then the integral of f of x dx from negative a to a equals 2 times the integral of f of x dx from 0 to a. Right? Okay? So, next issue. Let's do something else. Let's do this one. If I give you integral of x cubed from negative 4 to 4. Okay. What's the antiderivative of x cubed? X to the 4th over 4. And if we want to, we can pull the 1/4 out front, and we can just do this as 1/4 times x from negative 4x to the 4th, from negative 4 to 4. You probably already see what's going to happen, right? If we do it this way, and I leave that 1/4 out front, I just end up with getting 4 to the 4th minus negative 4 to the 4th. What's that answer? 0. Yeah, because isn't negative 4 to the 4th the same thing as 4 to the 4th?
Yeah.
Okay, well, how in the world did we get 0 out of that? Now, let's look at this graph. All right, if I take a cube function and why did we do that? That's a little better. And I'm gonna, I'm not gonna go clear out the 4s. Just assume this is 1, 2, 3, 4. Okay, so there's the area to the right of the y-axis, and here's the area to the left of the y-axis. That's not it. There's something else going on here. If they add up to 0, that tells us something about the way that we reckon area. I know that sounds like an old timer. I say that minor or something. I say reckon. That's what we say in math. The way we reckon area, the way we calculate area or add area, is we say the area is positive if it's above the x-axis or negative if it's below it, right? Okay. Now that might seem a little weird, but that's completely consistent with what we were talking about yesterday, for example, like with work, right? If you think about work, when are you doing positive work on something? You're doing positive work on something if you're applying, if the force is positive in the direction of the displacement, right? I would be doing negative work on the object if I were pulling on an object and sliding that way, slowing it down, right? Because what's the work energy theorem tell you? Net work equals what?
Force times displacement.
Well, no, there's much more elegant way of thinking about it.
It must be in the same direction.
No. It has anything to do with direction. Net work equals, you guys know the changing kinetic energy? You guys talk about that? Okay. That's the way, it's a really cool way to deal with work when you talk about dealing it in terms of an energy budget, because then you don't have to worry about any vectors, right? So doesn't that make sense? If you think about work in that sense, when I push on an object, and I guess more for physics types here, if I push on an object in the same direction as its displacement, what am I doing to its overall speed?
Increasing.
Okay, well, it's positive, right? Because kinetic energy is increasing. If I pull on it while it's moving in that direction, I'm robbing it of speed, and so I'm reducing its kinetic energy, right? So then that makes sense in terms of our calculus, doesn't it? If we're looking at force on the vertical axis and displacement on the horizontal axis, well, if the object is moving in the positive direction, if the displacement is positive, then if I'm pulling against the object, it's a negative force, and so the force would be considered negative. There you go. The area that we'd add up under that force displacement graph is negative, and the work is negative, right? You get the idea? They work. I mean, so this makes sense. It's completely consistent, even though it might seem bizarre at first. Okay, how about this one? So what's the moral of that story, though? We could say this. If we can come up with another little corollary here. If f of x has odd symmetry, then the integral of f of x dx over symmetric limits is always what? Zero. Those are easy, right? That's a great one. This one's useful. Because a lot of times you can at least take pieces of a function that have, if it's a function that has more than one term, if you break it up into terms, even if it's a complicated function, sometimes pieces of that function will have odd symmetry. And you can just get rid of them when you're summing, when you're doing an integral over symmetric limits there, right? So that's super useful. Okay, how about this one? How much time we got? Oh man, I got time. I'll try it. How about this? What's gonna happen if we do, what's one we've already done? Integral of x squared dx. Instead of going from 1 to 4, what if we go from 4 to 1? Doesn't that just give me x cubed over 3 from 4 to 1, which is going to be 1 cubed over 3 minus 4 cubed over 3,
64.
which is negative 63/3, which is negative 21. Okay? So what's that tell you then? If we add up area in the wrong direction, if we add from right to left, we're adding up area backwards. So we reckon area as positive from left to right and above the x-axis. Okay, so we come up with one more little corollary then. We could say that the integral of f of x dx from b to a is the opposite of the integral of f of x from a to b. Okay? And that's also a convenient thing to use sometimes. Okay, is that enough math for one period?
No.
Whew.